Hello, I'm Professor John Kelly, and this is the Weber Auto YouTube channel. In this episode, we will be looking at the low voltage charging systems of the 2024 Toyota Prius plug-in hybrid, also known as the Prime here in the United States. Toyota has quit using the word Prime because it was confusing for people not understanding that that is a plug-in hybrid electric vehicle designation. So the one we have here is labeled Prime, as you can see here in this photo. And as you can see, there's a door on the right rear fender that, when opened, allows you to plug in the charge cord for the high voltage battery on this car. There are four main parts of the low voltage charging system on this car. We have the high voltage battery that's under the vehicle. We have the inverter with converter that's under the hood. We have the low voltage battery itself that's in the rear hatch area. And then we have the onboard charge module that's in the rear hatch area that's used during charging of the high voltage battery. So let's find these parts on the car and then we'll learn how to test them. The first part we're going to see is the high voltage battery, and it is actually under the vehicle for the first time on a Toyota Prius. Okay, as you can see, underneath the Prius, we have removed all of the undercar covers. So normally you can't see the engine and the transmission here. You can't see the pipes going down the driver's side there and the orange cable going down the passenger side. But as we move towards the rear of the vehicle, this big black box that you see right here is the high voltage battery. And as I mentioned before, this is the first time that they've put a battery under the vehicle in a Prius. Prior to this vehicle, the batteries were always inside the vehicle and were air cooled. Well, this battery is not air cooled. This is a refrigerated battery, very similar to some of the BMW batteries. So we have an orange connector right here that you can see that has two wires connecting to it. That is the high voltage connection that goes from the battery up to the inverter and with converter under the hood. The little orange wired connector to the left of that is where the current comes in when you plug in your charge cord from the onboard charge module. And then the black connector on the right there is our low voltage connection that has all the power and ground and data communication and so on. And then these two pipes on the right hand side are the refrigeration pipes. So we have a high pressure line on the left, a low pressure line on the right, and we use refrigerant, just like in the air conditioning system, to remove heat from the battery. So this is a very unique battery for Toyota, and I'm going to be removing it and taking it apart and exploring it in a future video. But for now, let's follow the large orange cable from the battery to the front of the vehicle, where it's going to come up and go up under the hood where it connects to the inverter. Okay, the next part in the low voltage charging system is called the inverter with converter. The converter is the DC to DC converter. The job of the DC to DC converter is to take high voltage from the high voltage battery and step it down to a low voltage to keep the low voltage battery charged and to keep the low voltage system operating on the vehicle as you drive around. Okay, with the hood open, if we go to the driver's side of the engine compartment, this big rectangular box that you see right there is the inverter with converter. The inverter portion that drives the electric motors in the transmission is the top part of it. The DC to DC converter is in the bottom part of it. And the DC to DC converter has an output wire. You can see right here, I've got it labeled DC-DC wire, and that comes right over to our underhood fuse box, where if you take this cover off, it feeds power to the underhood fuse box and as a connection that goes all the way to the back of the vehicle to the low voltage battery. Now while we are here, there's a red jump start terminal right there. If we flip that open, you can see there is a metal tab right there that you can put the positive jumper cable on if you ever need to jump start this vehicle. So that is the jump start terminal positive. The negative cable for the jump start can go right here on the side of the inverter. The entire inverter with converter assembly housing is chassis ground, or you could go somewhere like that bracket right over there for your negative cable for jump starting. Okay, I have two inverters with converters built into them for Toyota Priuses right here. This one is from the 4th generation Prius, which ran from 2015 through 2022. And it has the inverter portion in the front that has 3-phase electrical connections, these 6 wires right here, 3 wires for each of the 2 electric motors that drive the electric motors and move the vehicle down the road on electric power and assist the internal combustion engine in providing power at different gear ratios to move you down the road. But in the bottom of this inverter with converter, if we were to take this panel off right here, is a part called the DC to DC converter. And that part is the second part of our low voltage charging system. And it receives high voltage right back here, this input from the high voltage battery, and then it steps it down to a low voltage to charge the low voltage battery and keep the low voltage system operating as you drive down the road. On the 4th generation Prius, you could change that DC to DC converter if it went bad. Now, right here I have the 5th generation Prius converter, this is a 5th generation Prius. It's just the plug-in hybrid version of it that Toyota calls the Prius Prime, as we've discussed earlier. But it also has the inverter portion that drives the electric motors in the transaxle in the top here. And you can see the 2 sets of 3 wire outputs there to drive the 2 electric motors with 3-phase power. The DC to DC converter is in the lower portion of this housing, and this black wire that you see right here is the output of the DC to DC converter. It has a little cover right here that you can lift up and see the output terminal right there. And then this came up and connected to that underhood fuse box. And then there's another wire that goes to the back of the vehicle to feed power to the low voltage battery and keep it charged. So the big deal about this inverter with converter is you can't service the DC to DC converter. It's all one piece now. And this is the first time Toyota has done this on the Prius. All of the previous 4 generations of the Prius would allow you to change the DC to DC converter. This one you cannot. It's the entire assembly that has to be changed. So just a word of warning, always follow the jump start procedure instructions in the owner's manual to jump start your vehicle, this vehicle here, and see if it's even allowed to jump start another vehicle. Because if you hook the cables up incorrectly and you damage the DC to DC converter here, you're going to have a very expensive piece to change. So this is one of 2 DC to DC converters on this vehicle. There's another one that's used when we plug in the charge cord to the side of the vehicle to charge the high voltage battery, and it's called a sub DC to DC converter. Let's go look at it next. Okay, here in the back of the Prius, over here on the driver's side is the onboard charge module. This is the module that receives power when you plug in your charge cord to the side of the vehicle, and it charges the high voltage battery with it. It also provides power to some electrical sockets here on the side of the rear hatch area, and there's an electrical socket at the back of the center console over there also. But the third thing it does is while you're charging the high voltage battery, it uses what's called a sub DC to DC converter to keep the low voltage battery from being discharged and to keep the system alive while it's charging. Now, also while we are here in the back hatch, we have access to the fuel pump, the fuel tank access panel right there. That next opening is the high voltage manual service disconnect lever, the MSD, that Toyota has called the service plug grip for many years, but MSD is the official SAE term for that. And then over here on the passenger side in the right rear of the vehicle is our low voltage battery. We have the positive post of the battery over here at the rear of the vehicle and the negative post right there. The negative picks up its connection to chassis ground right down here. You can see there is a vent tube right there. This battery is not an AGM battery, an absorbed glass mat battery. This is a standard lead acid battery, but it is vented because it's inside of the passenger compartment. So if we look at the positive terminal there and follow this black wire, it goes into this orange taped harness, which it doesn't need to because it's not high voltage, but it goes into the same harness that goes up to the front of the vehicle and eventually connects to that underhood fuse box that we looked at earlier. So the low voltage battery is the third component of our low voltage charging system, and then the onboard charge module is the fourth component of our low voltage charging system. Okay, whenever I check the low voltage charging system on a hybrid or an electric vehicle, I typically will use an amp clamp. And this amp clamp here is from Fluke. It's the 375 FC. The FC stands for Fluke Connect. And that's a smartphone app that you can download for free. And this allows you to view the output on this meter without having to be at the meter. So I'm going to be monitoring 3 different meters at the same time on this app. And so to get that set up, I need to turn on the clamp meter here. To prevent it from automatically shutting off, I'm going to hold in the inrush button while I turn the rotary dial to amps DC, and then I'll click the hold button on the side here, and you see the letters P off right there on the screen, indicating that the automatic power off has been disabled. Now there's a Fluke Connect button right here. If I push that, it enables Bluetooth communication with the smartphone app. And so I will click connect and capture measurements on the Fluke Connect meter. It's already picked up this output from this meter, so I'll click on that and give it a minute to establish a connection. And there we go. We have 0.4, 0.3 amps showing up right there. That's what's called the DC offset. So we need to zero our meter by pushing this little yellow button right here. And now we have 0 amps. And we're ready to measure the output of the DC to DC converter with this amp clamp. So I'm going to do this underneath the hood. And so this is going to go around that black wire that comes out of the DC to DC converter on the inverter with converter assembly and goes to that underhood fuse box. So I'm going to connect it right now. Okay, as you can see on the Fluke Connect app, we are reading 0 amps. And that's because the car is off. There's no output from the DC to DC converter. But I've got the trunk open, I've got the rear hatch lights on. We are drawing current out of the battery, and so now let's take another amp clamp and we'll go back to the low voltage battery and see how much current is coming out of the battery. Okay, here in the back of the vehicle with our low voltage battery, I have another amp clamp that I'm going to connect. So I'll turn it on the same way. You select this button to add another device. It has picked up that device already, the second amp clamp, and give it a minute to synchronize. There we go. We're showing 0.7 amps. I'm going to zero the meter, get rid of that DC offset, and now I'm going to clamp this around the negative cable, and we'll see how much current we have leaving the battery at this moment. So we have a negative 0.9, 0.8 amps. So we are discharging the low voltage battery at this time. So if we see a negative amperage, that's battery discharge. If we see a positive amperage, that's battery charging. All right, now I also have a Fluke multimeter. This is the Fluke 1587 FC. And I use it for a number of things on hybrid and electric vehicles, but today I'm just going to use it as a regular multimeter. And so I'll turn it to DC volts, press the Fluke Connect button. I'll go to the smartphone app, add one more device. It's picked it up right there. So now we have our third device, and I'm just going to connect to the positive and negative side of the low voltage battery back here. All right, I'm reading 12.18 volts on our low voltage battery, which is pretty low. I've been abusing it here. shooting this video, so that's pretty low. So we are ready to see what happens. This is car off. We're ready to see what happens now when we turn the car on. When we turn the car on, the DC to DC converter should start working, and we should see this voltage jump up from the 12.8. It should go up to around 14 or so volts, and then we should see the current going into the low voltage battery go up. We should see the current leaving the DC to DC converter, the top parameter here, go way up also, because the car takes a certain amount of current just to operate, and then on top of that we have to recharge this battery. So let me get the car turned on now. Stepping on the brake pedal now. Notice that made our low voltage battery current go up, and now I'm going to push the power button, the start button. Notice immediately our current going into the battery went up to 36 or so amps. The DC to DC converter output went as high as 84 amps initially as we turned the car on. Okay, as you can see here, with the car turned on, the DC to DC converter output is roughly 29 amps. The current going into the low voltage battery is around 15 amps, and our low voltage battery voltage is 14.16 approximately. The current going into the battery will decrease as the state of charge of that low voltage battery increases. So as the battery charges, the amount of current it needs decreases. That's normal. So for Toyota's official procedure for checking the low voltage charging system, they tell us we have to wait until that low voltage battery current is less than 10 amps. Okay, here we have the Toyota Global Techstream Plus software, and I have it connected to the data link connector through a Mongoose Toyota adapter, and I'm going to click Connect to Vehicle. It uses the vehicle identification number to identify the vehicle. I just double check to make sure everything looks right, and yes it does as far as the information. So I'll hit the arrow to continue. And then we are going to go to System Select and select the Hybrid Control Module right here. So this is the computer in charge of the low voltage charging system on this vehicle. So it defaults to showing us diagnostic trouble codes, of which there are none. So up here we will select Data List, and as you can see it shows us a giant list of data that we can see on the hybrid control module. But Toyota has narrowed down and made some custom data lists. There's one right here that we can select called the DC to DC converter data list. Notice that shortened it, shortened the parameters quite a bit. There's a lot of things to see here. But out of all of these things that I want to see, really I only want to see the high voltage battery voltage and current and the auxiliary battery voltage and current. Everything else doesn't help me in the low voltage charging system check. So I made my own custom data list just for this lab in my classes. I call it the DC to DC converter lab. And as you can see, it ignores everything except the 4 data parameters that I want to look at. So right now, it shows us our high voltage battery voltage is 289 volts, and we're supplying about 1.2 to as high as 1.5 amps out of the high voltage battery to feed the rest of the vehicle. The car is on, but it's in park. We're not using any high voltage for anything except for the DC to DC converter here in the inverter assembly under the hood. So we've taken 289 volts in the DC to DC converter and stepped it down to 14.12 volts. That's a 20-to-1 reduction. So we've reduced the voltage by a factor of 20. That also allows our current to go up by a factor of 20 at a maximum. So right now our auxiliary battery current is 18 amps, and that matches what is here on our Fluke Connect app. It's reading 18.1 amps. But that's battery current. What we don't see here that I would like to see is the DC to DC converter output current. And so we can see that here on the Fluke Connect app at 32.6 amps. So it is a data parameter that they're not showing us on the scan tool. But that's something that we want to watch because the DC to DC converter is rated at a maximum of 130 amps on this vehicle, and we are at 32 amps right now, minus the 18 going into the battery. So that means if the battery, the low voltage battery, were fully charged, it would only take 16 amps to run this vehicle, to have this vehicle powered on and not be driving. So our low voltage battery current is still quite high, 17.9 amps. We're just going to let it keep charging that low voltage battery as we turn on additional loads. So the official Toyota procedure for checking the low voltage charging system is to turn on the electrical loads inside the vehicle one device at a time and watch the current come up. And with everything turned on, low voltage inside the vehicle that we can find, the output should be less than the 130 amps from the DC to DC converter. The voltage should be within specification, which is above 13 volts at the maximum 130 amp output. So now we're going to turn on every electrical load that we can find inside the vehicle and try to load test the DC to DC converter and see how high we can make that output current go. Okay, the first thing I need to do to load test this vehicle is to turn off the automatic headlights. That way we can turn on the high beam headlights. And now we will turn on the high beam headlights. We'll turn the lights as bright as they can go. So we're roughly at 31 amps before turning the high beams on. We are at 36.9 amps out of the DC to DC converter with the headlights on high. All right, the next thing we want to turn on is the steering wheel heater. Notice we're up to 41.9 amps. And then the next thing is the windshield de-icer. Now we're up to 48 amps of DC to DC converter output. Okay, so now I'm going to turn on the 120 volt outlets in the rear area of the vehicle. We're up to 48 amps. So we're up to 61 amps with the rear defogger turned on. So here's both front seat heaters and the climate control. We're up to 72 amps. We have 75 amps now. With the climate control running on heat, we have the heat pump running, so we have the radiator fan pulling in air to capture the heat energy from it. So we're up to 79 amps of current. Okay, now I'm going to start the engine by turning off the EV mode. Went to hybrid mode, there we go. 91 amps, 92 amps, because we have the fuel pump and everything electrical, the fuel injectors and ECM, all involved in having the engine running. So we got as high as 96 amps there. Okay, so with everything turned on, we got as high as 96 amps of current leaving the DC to DC converter. Notice we still have 15 going into the low voltage battery in the rear hatch out of that, which means our low voltage battery is still charging. It'll be a while because it was pretty low. It was down to 12.2 amps or 12.2 volts. But we were able to turn on all low voltage accessories that we possibly could, and still we are below the 130 amp maximum output. Now, there are electrical sockets back there that could have electrical loads put on them. I believe they were rated at 1200 watt each, and so there's additional load. We have USB sockets back there. I'm not sure what their load is, but there are additional loads that can be plugged into the vehicle. And so to have a DC to DC converter that's rated for a higher amount of current is really good. So this is the official load test procedure for Toyota. At this point, they would tell us, make sure that the battery voltage is above 13 volts, and we're at 14.11 volts. Our current is slowly going down in that low voltage battery to 14.6. All right, now there's another way to load test the low voltage charging system, and that's with a carbon pile load tester. So let's look at it next. Okay, this is the carbon pile load tester that I use to stress test the low voltage charging system to get the maximum output from the DC to DC converter on all of these hybrid and electric vehicles. This was actually a recommended procedure for the Chevrolet Bolt EV and the Volt. It was to use a carbon pile load tester, and the idea is to put maximum load on the DC to DC converter output while monitoring its output voltage. If it can put out the maximum current that it's rated for and keep the voltage high as it needs to while it's putting that out, then the DC to DC converter is probably in good shape. As long as your high voltage battery is in good shape also. Don't forget, the high voltage battery is what feeds power to the DC to DC converter. So if you have a discharged high voltage battery, it's very possible to have your low voltage charging system stop working. So let's get this hooked up. This is from Associated. This is a company here in the United States, and it is model 6039. And I'll put a link to that in the video description as to where I got that. Okay, I've connected the red clamp from our carbon pile load tester to battery positive and the black clamp to our chassis ground connection here in the back of the rear hatch. And if we go to the front of the load tester here, there's a red switch to turn it on, which I've already turned it on. And we have an amp meter here and a voltmeter here. The amp meter tells us the load that is being put on the carbon pile discs in this tester, and then of course the voltage is just the system voltage. This Prius Prime has a maximum output of 130 amps, but we've got to remember that the vehicle needs current just to operate, so we're not going to put a 130 amp load on the carbon pile tester. Right now we are already drawing 32 amps of current from the DC to DC converter to operate the vehicle, of which 12.5 amps is going into the low voltage battery. So let's just call it 32 amps is our DC to DC converter output right now. If we are rated, if the DC to DC converter is rated at 130 amps maximum, and we're already using 32 of that, that means we are going to load the carbon pile tester to 130 minus 32, which is 98 amps. So I'm going to turn this knob over here and load it until we get to around 98 amps. We will also watch our Fluke Connect app and make sure that we don't exceed for very long, if at all, the maximum output. So here we go. We're up to 40, 50, 60 amps on the DC to DC converter. We're up to 80 amps on the carbon pile load tester. Whoop, too high. All right, we are at 100 and coming down a little bit. Okay, 122 amp output from the DC to DC converter. At the same time, we have 14.1 volts output. That is really good. So now I'm going to back off on our carbon pile load tester. So that's exactly what you want to see when you carbon pile load test a DC to DC converter. But one of the problems with this that you need to be very careful of is you saw that I overloaded the DC to DC converter just for a few seconds there. It's real easy to put too much of a load on the carbon pile load tester as you're doing this. The Toyota method of just turning on all the accessories is a safe way to go, but it doesn't necessarily check the maximum output. I really like this method of using the carbon pile load tester because it's quick, and as long as you're aware of how much current the DC to DC converter is putting out just to keep the car turned on, which we're still at 31.6 amps, and subtract that from the maximum output of the DC to DC converter, which finding the maximum output rating on these vehicles can be challenging. It depends on the hybrid or electric vehicle manufacturer as to where that information is found. But I've been able to find it on every vehicle that we have here in our hybrid and electric vehicle labs. So I really like this. It's a good way to go. I really like the Fluke Connect app. That's great for monitoring multiple devices at the same time while you're checking the charging system output. Now, why would you bother checking the charging system output? Well, what if your low voltage battery keeps going dead? It doesn't mean the battery's bad. What if your DC to DC converter has a problem? Then you would want to do some sort of a load test like this. What if it only goes dead while you're charging the vehicle with a plug-in charge cable? Then you would want to check the output of the onboard charge module here. We could monitor this exact same parameters here, except for the DC to DC converter output. We could monitor the battery, low voltage battery current, and the low voltage battery voltage when we plug in a charge cable. As a matter of fact, let's do it. Okay, I've got a charge cord here from a Tesla universal wall connector, it's called. It has a built-in adapter to go from the Tesla NACS connector to the J1772 connector that this Prius Prime has for a charge port. Notice that our Fluke Connect app is showing a negative 3.6 amps coming out of our low voltage battery, and our battery voltage is 12.77 volts. Oh, by the way, I realized I left the headlights on during the whole test here at the end. When I thought I'd turned off all the accessories, I totally forgot the headlights. That's why our output current was so much higher than it normally should have been out of our DC to DC converter. So now let's plug this into the charge port. Got the lock came down. We should get a green light right here if it's charging. There we go, green light indicates we're charging. And notice our Fluke Connect app now is showing 20 amps going into the battery, and our low voltage battery voltage is 14. But notice, wow, that's interesting. The DC to DC converter in the front of the vehicle is active. It's at 23 amp output. So very interesting. I was wrong. The fourth generation Prius, or the first generation Prius Prime, had a separate DC to DC converter back here in the onboard charge module. But this system is using the front DC to DC converter. This is just like if the car was turned on, but the car is off right now. So we've got 19.8 amps out of the DC to DC converter, of which 13.5 of those are going into the low voltage battery, which means we have about a 6 amp difference that's being used as we're charging the high voltage battery. Well, that's different than what it says in the Toyota service information for this car. But we've just proved that that's what's happening. And I wondered, because I couldn't find a larger output cable on the onboard charger back here, onboard charge module, where on the previous version it did have a larger low voltage output terminal. So I've learned something just through experimentation here with you on this vehicle. All right, well, this is the low voltage charging system check for the fourth generation Prius and the Prius Prime, or the plug-in hybrid version of the Prius. If you like this type of video, I would appreciate your support. There's a donation link to Weber State University's automotive department in the video text. Also, please subscribe, click that bell button, be notified of any new videos I produce. I'm trying to produce more videos now. I've been very busy with some other things the last couple of years, but I'm trying to get busy and get some more videos back out there, because this is what I really like doing. So anyway, thank you for watching, and have a good day.